Inference for proportions. In this program, we will review chi-square testing and the use of the crosstab. We'll also look at two-sample Z-testing and one-sample Z-tests and confidence intervals. Chi-square testing. We use a chi-square test of independence to see if there's a significant relationship between two categorical variables. One variable is an independent variable, and the other is a dependent variable. We already learned how to use crosstabs and conditional distributions to examine the relationship between two categorical variables. However, that was just an observed relationship or a descriptive analysis because it's tied only to our sample data. The chi-square test will tell us whether the relationship is significant. In other words, can we infer that the population would have the same relationship or similar one as we observe in our sample data. To start our chi-square test, we used our Unit 4 case Excel tool and set it up to examine the relationship between gender, which is variable 4, and the categorically coded amount charged, which is variable 8. And we've input our variable numbers and our category labels. By clicking the Worksheet tab crosstab, we see the results of our analysis. Our crosstab shows us the relationship between gender and amount charged. Here, gender is the independent variable and the row variable, and amount charge is the dependent variable. To observe the relationship, we can use the conditional distribution by gender. In other words, if a cardholder is male, what's the probability distribution of their spending category? Or if the cardholder is a woman, what's the distribution of their spending category? And you can see that these numbers are different. The difference between the two probability distributions tells us that the likelihood of spending in one or another category is affected by a cardholder's gender. The chi-square test of independence shows us that not only can we observe a relationship between gender and spending category, but the p-value for our chi-square test tells us that that relationship is statistically significant. Our p-value of 0.0166 is well below the 5% significance level. Therefore, in a chi-square test, we reject the null hypothesis of independence or no association between the two variables in favor of our alternative, which is that there is an association. The clustered bar graph shows us visually the comparison between the two conditional probability distributions we looked at on the previous page. So here, overall, we can conclude that gender does have a significant association with spending category. This is something that we observe in our random sample of 50 cardholders, but the chi-square test tells us that the relationship is significant. In other words, it is likely to hold throughout the entire population of our cardholder market. Now let's take a look at the two-sample Z-test for proportion difference. We're going to look at when to use the two-sample Z-test by comparing the Z-test against the chi-square test. We'll look at one main advantage of the two-sample Z, and that is it allows us to run one-tailed testing, whereas chi-square does not. It also provides us with a confidence interval of the difference in population proportions. To set up our two-sample z-test, I first input the independent variable number 4, which is our gender variable, and both category labels. What we're doing is we're creating two samples of data. One sample will be the men, and the other sample will be the women. Our dependent variable is the two-category version of amount charged. By inputting the success category 2, what we're doing is we're comparing statistically the proportion of men in our sample who are in the high category of spending, category 2, against the proportion of women in our sample who are in that high category of spending. So p hat 1 would be x over n. The number x would be the number of men who spent in category 2 out of n, the total number of men. P hat 2 would be the same for women, the number of category 2 spenders out of the total number of women. And once we run that, we get our two-sample Z results. Our sample information is interesting. We see that 60% of the men spent in category 2, 50% of the women spent in category 2. That's a difference p hat 1 minus p hat 2 of 10%. However, our margin of error is about 28%. So the confidence interval for the difference in the proportions of men who spend in category 2 and women who spend in category 2 ranges from a negative value to a positive value. And quite clearly, 0 is in the confidence interval. Therefore, we can conclude that there's no significant difference in the proportion of men who spend in category 2 and the proportion of women who spend in category 2. Running a different test and changing our independent variable to age shows different results. Here the age variable is recoded categorically into two groups. The low age group is below the mean, and everybody in the high age group has an age above the mean. Here we can see the two-sample Z results. Our sample information shows us that the high age cardholders, 22 out of 22, or 100% of the time, spend in category 2. The younger cardholders only do that 17.9% of the time. Assuming no difference as a test value, we could see that our observed difference, 82%, p hat 1 minus p hat 2, or 100% minus 17.9%, ends up 5.785 standard errors above 0. Of course, our upper tail p-value is 0 to 4 places. Here we can conclude quite clearly that the proportion of category 2 spenders among the older cardholders is significantly greater than the proportion of category 2 spenders among the younger cardholders. Finally, let's take a quick look at the Onesample ZTest and confidence interval. We'll look at when to use that particular test and how to determine whether we want a one-tailed or two-tailed test. And finally, we'll look at how to use the confidence interval to estimate a population proportion. To set up our Onesample Z, we first input a variable number 4, which is our gender variable, and the success category, or the category of interest for us now is the women. So I've input the category label F. What we're telling Excel to do now is to count X, the number of women, or in our data, the number of Fs, out of N, the size of our sample, which is 50. Now here is our Onesample ZTest results. Our sample information shows that 30 out of 50 are women, which is a sample proportion p-hat of 0.6 or 60%. Our z-test will compare the sample proportion of 0.6 against any test value that I input here. I'm setting up a null hypothesis, which is simply a hypothesis statement about the population proportion, a what-if scenario. So if the population proportion is 0.58, what is the significance of the sample proportion of 0.6? Here I can see my upper tail p-value is quite a bit higher than my level of significance. Therefore, here I would conclude that there's no significant difference between my sample proportion and the test value for the population proportion of 0.58. To show a different result, what if our null hypothesis were to be that the population proportion of women in our market is 45% or 0.45. Now the same sample information, which gave us a p-hat, a sample proportion of women equal to 0.6, now we get a significant result. Our test statistic of 2.13 would show us that the sample proportion of 0.6 is more than 2 standard errors above the test value of 0.45. That only occurs 1.6% of the time at random. Therefore, because this probably didn't happen at random, we conclude that our sample proportion is significantly greater than the test value of 0.45. In this case, we would reject that null hypothesis that p equals 0.45 in favor of our upper-tailed alternative. This concludes the program Inference for Proportions.